Guys, welcome back to TechDose, and in this video we will look at divide nodes into the maximum number of groups problem, which is from Leetcode number 2493. This is based on bipartite graph. A good problem to solve after watching this is to actually solve the possible bipartition problem, which is from Leetcode 886. I have already provided the video link in the description below. So let's now read the problem statement. In this problem, you are given a positive integer n representing the number of nodes in an undirected graph. The nodes are labeled from 1 to n. You are also given a 2D integer array edges. Edges at I shows ai, bi indicates that there is a bidirectional edge between the nodes ai and bi. Notice that the given graph may be disconnected. Divide the nodes of the graph into m groups, which is one based indexed, such that each node in the graph belongs to exactly one group, and for every pair of nodes in the graph that are connected by the edge ai, bi, if ai belongs to the group with index x and bi belongs to the group with index y, then the absolute difference between y and x should be equals to 1. That means if there is an edge between ai and bi, then they must be present in two adjacent groups. Return the maximum number of groups, that is the maximum m, into which you can divide the nodes. Return -1 if it is impossible to group the nodes with the given conditions. Now if you look at one of the given examples, then in this case we are given n equals to 6. That means we have 6 number of vertices and all the edges are given in the form of edge list. Now from the edge list you can construct the adjacency list and get the graph, and this is the given graph. In this case I can just group them into 4 different groups and still follow the condition so that there is no edge between two nodes in the same group. And why did I say that? Because let's say that if you had an edge between this 3 and 6, then according to the condition, the index of the group number, the difference between the group number for 3 and 6 must be equals to 1. But they cannot lie in the same group, right? So that is why, according to the given condition, that if there is an edge from ai to bi, then ai and bi should be in separate groups and they must be in adjacent group in such a way that ai is in group x, bi is in group y, and the difference between them, the absolute difference x minus y or y minus x, must be exactly equals to 1. So according to this condition, we can deduce that there will be no edge between two nodes within the same group, and if there is an edge between two nodes, they must be in the two adjacent groups. Okay, so once you have understood all these conditions, we need to maximize the count of group. I will be exactly showing you all the conditions while solving. So in this case, the maximum possible groups are 4. You cannot make more groups, but yes, you can make less groups. I will be showing you later in the explanation. Now if you look at the constraint, then here the n value is less than equals to 500. This means the number of vertices maximum will be 500 and the edge list will be maximum of length 10 to the power of 4. Okay, so this will be very essential for us to actually decide what will be the expected runtime, because finally we have to write the time complexity, which must have computations less than 10 to the power of 8 to run within 1 second. Okay, so this is very important criteria to look at. Now there is at most one edge between any pair of vertices, right? And ai, bi are not same, they will always be different. So let's now understand something about the bipartite graph before looking at the solution. A bipartite graph is a graph whose vertices can be divided into two disjoint and independent sets u, v, such that every edge connects a vertex in u to one in v. Well, what is the meaning of this? Let's take a given example of the graph. This is in the form of a tree. You know that all the trees are a graph, right? So this is a graph given with 4 nodes and 3 edges. Now in this case, I can exactly divide this into two particular group in such a way that group u will be having 0, 3 and group v will be having this 1, 2, so that there will always be an edge from the node in group u to the node in group v and vice versa, but there will be no edges in between the two nodes in the same group. That will not be possible. Okay, so if this can be done for a given graph, then such kind of graph are called bipartite graph. So there are two important points to remember: the disjoint and independent set. If you consider about a disjoint set, then the word disjoint means non-overlapping. So this means that a node if it is present in set U, it cannot be present in set V side by side. A node must always be present in exactly one set. That is the meaning of disjoint set. Now, what is the meaning of independent set? It means that there should be no edge between two items in the same set. So if you consider this 0, 3, you cannot have an edge between them since they lie in the same set. So if your graph can be exactly divided into two separate groups in such a way that these two groups are disjoint and independent, then we can say that such kind of graph are bipartite graph. And all the trees, by the way, follows the conditions of bipartite graph. So all the trees will be bipartite graph. Now, if you look at the second example, in this particular case, what I can do is I can take this 0, 2 and put it in set U, and take this 1, 3 and put it in set V in such a way that there will be no edge between two nodes in the same group, either in U or in V. And if there is an edge, it will always be from a node in U to a node in V and vice versa. And you will see that there is no overlap of the nodes. That means a node is exactly present in either U or V, but not in both. So this is a bipartite graph. Even though there is a cycle here, it is a bipartite graph, right? Now, if you look at the example number 3, in this case, if you put this 0 in, let's say, U, and this 1 in V, definitely you have to place this 2 in V as well, because there is an edge between this 0 and 2. Therefore, they cannot be placed in the same group. Otherwise, they will not be independent set. So if you have put this 0 in U, then I am forced to put this 1 and 2 in the V. Now, since there is an edge between this 1 and 2, therefore, there is an edge between two nodes in the same group V. So it is not an independent set. It is not an independent set. And therefore, even though it is a disjoint set, it is not an independent set. So I will say that this is not a bipartite graph. This is not a bipartite graph. So all the graphs are bipartite except the ones having the odd length cycle. Even if you have an even length cycle or multiple even length cycle, it does not matter. But if you have an odd length cycle in the graph, then this graph will not be a bipartite graph. So remember that all the graphs are bipartite, all the trees are bipartite. Only the graphs with at least one odd length cycle are the graphs where the bipartite is not possible. Okay, it is not a bipartite graph. So once you have understood the bipartite graph, let's see how to find if the graph is a bipartite graph. So we can simply do that by using the BFS and the state or the coloring technique. So in this case, I will be taking a multi-component graph. Okay, because the problem statement also has multi-component test cases. So I will be taking multi-component graph. So in this case, I have total of 7 nodes from 0 to 6. So I will be marking a state array. This is similar to how we define a visited array. Okay. In the visited array, we just have 2 states, and that is why we take it boolean to be true or false or 0 or 1. While in the state section, I will be using 3 colors because we have 3 states here. Okay. So this will be of integer array type. Now in this state, I will be marking all the node values with 0. This means none of the nodes are visited. So state 0 means it is unvisited. And then I will be having 2 other states, a positive 1 and a negative 1. The positive 1 means the corresponding item belongs to group 1, and the negative 1 means the corresponding item belongs to group 2. Okay. Now let's see how to process it. Now I will be starting my BFS from node 0. Well, you can start your BFS from any node. You are not required to always start from 0, but since it is the lowest number, I generally prefer to start with the lowest number. So how to do BFS? First, I will be pushing the source node or the start node into the queue, and then I will be changing the state because this is not a visited node, right? This is not visited. So what I will do is I will push this into a group. Let's say that I write here -1. So this means that this has been pushed into group 2. So the state here is -1. Okay, state here is -1. So if this is pushed in group 2, then what is expected out of the adjacency list of this 0? In the adjacency list of 0, you will find 1 and 2 to be present. So all the you can just traverse through this adjacency list and try to place them in the different group. So I will be placing them in group number 1. So for 1, I will be placing it in 1, and for 2, I will be placing it in 1 as well. So this means that I am also marking 1 and 2 as visited, and I am also placing them under the same group, which is the positive group, the group number 1. Okay. And once I am doing that, I have to push this into the queue as well. So 1 and 2 are pushed into the queue. And now we have processed our 0 node. After this, what I should do is, I will be taking out the next node 1. Okay, 1 has been taken out. So for 1, I will be checking the adjacency list. So the adjacency list of 1 will be having 0 and 3. So for this node, for 1, if the adjacency list is having 0 and 3, then I will check, is 0 marked or not marked? Yes, it is marked already, and it is having a value -1. So if it is marked, then I will be checking the current node 1 is having a group, a positive group 1. So what is expected out of 0? It is expected that it is present in the other group. So yes, the value is -1 and this is 1. So it is present in another group. So this is fine. We will not do anything for it. Otherwise, if they are present in same group, then I will be returning false for it, or -1, right? Now, what about this 3? This 3 is not marked. So let's mark it. With what value will you mark? You will mark it with -1. Okay, so I will be marking it with -1. So how are we alternating between the values? When we have a positive 1, I want to mark with -1. And when I have a -1, I want to mark it with +1. So you can just take whatever is the value, you just multiply it with -1 value. So if this value happens to be 1, then the result will be -1. If this value happens to be -1, your result will be 1. So this is how you can alternate by just multiplying with -1 value. Okay. So now we are clear with 1, and since we have changed the state of 3, I will be pushing it into the queue. And now the next node to be processed is 2. So let's take out 2, its value is 1. So in the adjacency list of 2, we have 0 and 3. So what is expected at 0? -1 times 1. That means it is expected to have -1 value here, which is fine. For 3, it is expected -1 value, which is fine. So nothing will get inserted because we had already visited this 0 and 3. Okay, so we are done with this 2. Let's take out this 3. So if you take out 3 again, it is marked, and if it is marked, go to the adjacency list for 1 and 2. They are as per expectation because 3's value is -1. So the adjacent value should have one value. They should be present in different group, and that is completely fine. Now we are done with our BFS, and the queue is also empty. Okay. Now this does not mean that we have checked our entire graph, because this is a multi-component graph. So we have to continuously be on the lookout and see if there is any unvisited node. You have to restart your BFS again. So we will be again calling the BFS, and we will be pushing the new source node, which is 4, right? I will be exactly showing you in the code how to do this. But let's say that we will be pushing this 4, and let's assign it a certain group, and let's assign it a group -1, which is group number 2. Now I will be iterating through the adjacent node 5 and 6, and I will be checking. For 5 and 6, they are not visited. So what is expected? -1 times -1. So it is expected to be in the positive group. That means the other group, 1 and 1. So mark them with 1 and 1 value and push 5 and 6 here, right? And since we have processed 4, we will be removing it definitely. And now we will be processing the next node, which is 5. So take out this 5. Take out this 5. If you take out this 5, check out the adjacent values 4 and 6. What is expected at 4? If the value is 1 at 5, it is expected to have -1, and it is fine. And at 6, it is expected to have -1, but there is 1. So this means there is an odd length cycle, and therefore this is not a bipartite graph. Okay, this is not a bipartite graph. You will return -1. But let's assume that you did not had this edge. You did not had this edge. Then 5 and 6 are not adjacent. So only 5 will be checked against 4, and it is fine. We will be taking it out. And now we will be processing this 6. Take out this 6. And what is the value at 6? 1. So what is expected at 4? -1. So it is fine, and there is no other adjacent node. And so once you have processed all the nodes, and since you could not find any discrepancy, that means no two adjacent nodes are in the same group, therefore you will say that it is a bipartite graph. Okay, so this is how you check if there is a odd length cycle within a multi-component graph or in a single component graph using the BFS with the state management or the 3-color technique. Okay, where we used 0 as unvisited node, 1 to be a positive state, which will be like group 1, and -1 to be a negative state, which means group 2. Now if you think about the time complexity, we are just doing simple BFS here. So the time complexity will be V plus E, and the space complexity will be order of V. because the state size was order of v, and the queue size can go to order of v because it can contain all the nodes into the queue, right? Now let's look at the code for how to find if a graph is bipartite graph. In this code, we have a utility function check bipartite graph where we are given the adjacency list and the value n. N is the number of vertices. Now I am defining a state of size n plus 1 because the vertices in the given problem will go from 1 to n. So if I define n plus 1, then it will go from 0 to n, and the 0th index will never get used. Now I am using a for loop. Now this for loop will maintain that in a multi-component system, if we have already done a BFS on a certain component, if we have already done BFS, then the other component actually gets covered. Once a single component gets covered, we do not lose track of the other component. If it is just a single component, then we can perform only one time BFS. But if it is multi-component, we have to check by going to each node if they are traversed or not traversed. Now state at I equals 0 means it is untraversed, it is unvisited. And we are checking, is the current component a bipartite component or not. So we will be actually sending the adjacency list, the state array, and the index I from where we are starting the new BFS for the new component. So in this multi-component system, one time maybe I will start at 0, and one time again I will be starting at 3, 2 times BFS. So the number of times the BFS will be running is equals to the number of components. Okay, number of components. So if you look at for one component what to do, we have written a is component bipartite. We are taking the adjacency list, the state array, and where to start the BFS. So this is just the simple BFS, right? In this BFS we will be pushing the start node and set the state to 1. That means we are starting at 1. In the dry run we were starting with the value -1. You can start with any group, 1 or -1, it does not matter. Now we have to apply BFS, and this is simply taking out the front of the item from the queue and then finding out the neighbors. This is from the adjacency list, and checking if the neighbor is unvisited, then mark it with a state. So if the current state is 1, then the adjacent state will be 1 times -1, which becomes -1. If the current state is -1, then the adjacent state will become -1 times -1, which is 1. Okay, so this is how the alternate assignment is done. Now after this it will be pushed into the queue. But if the adjacent node is already visited, then the adjacent node and the current node and the adjacent node should not have the same state. Okay, because if they are having the same state, then this means that two adjacent nodes are in the same group. But according to the problem statement, if there is an edge between AI and BI, then the group difference, that means if this belongs to group X and this belongs to group Y, then Y minus X mod must be exactly equals to 1. But if they belong to the same group, then how can this be 1, right? So that is why we have to do this check. This is the simple bipartite graph check. Okay, so if the neighbor node and the current node has the same group, then we will return false, saying that it is not a bipartite graph. And as soon as we figure out that a component is not bipartite, then definitely the entire graph will not be bipartite. We will be returning false. So for an entire graph to be bipartite, all its components must be bipartite, every component. And after every component check, if every component of the graph is bipartite, I will be returning true, saying that the entire graph is bipartite. Okay, so this is how you do the check for a graph being a bipartite graph or not. Okay, so this was the prerequisite for this problem. Now let's see the problem deduction. In this particular problem, let's take the example which was already given on Leetcode. So in this case, as you know, we were able to divide the given example into 4 different groups. Okay, now according to the problem statement mentioned, there will be no edge between the 2 elements of the same group, because if there is an edge between 2 elements of the same group, let's say 4 and 5, then they cannot belong to the same group. Otherwise, if this 4 belongs to group X and this belongs to group Y, then Y minus X cannot be 1 if they belong to the same group, right? So that is the concept of independent set. And if you see, an element only occurs in one group, because if 4 is present, it can only be present in group 4. It cannot be present in group 3 as well as group 4. An element will only be present in exactly one group. So this is the concept of disjoint set. So this problem is combining the concept of both independent set and the disjoint set. And you know that a bipartite graph is a graph which is independent as well as disjoint. So that is why this problem is a bipartite graph problem. Okay. Now, since you know that this problem is a bipartite graph problem, and in the given example here, if we were able to divide it into certain number of groups, the max number of groups being 4, then I can always say that since this graph is a bipartite graph, I will always be able to divide the vertices into 2 independent and disjoint sets. Okay, what is the meaning of this? I can put all these nodes into 2 groups U and V in such a way that there will always be an edge from a node in U to a node in V, or vice versa from V to U, but there will never be an edge in between 2 nodes in U or in V. That is the meaning of disjoint and independent set. So in this case, I can put this 0 in, let's say, group U, 1 in group V, 2, 3 in group U again, and 4, 5 in group V. And you will see that all the edges occur between 2 nodes. In one will be in U and another one will be in V, and there will be no 2 nodes in the same group where you have an edge. Okay, so that is why this is a disjoint and independent set. Okay, so since we already knew that this problem is about bipartite graph because of our logical deduction of the independent and disjoint set, so I can make this kind of distribution. So it is always possible to divide a bipartite graph into 2 disjoint and independent set. Okay, now I think it is clear why this problem is a bipartite graph problem. Now in this particular example, it will not be possible to divide it into 2 separate groups U, V, so that they are independent as well as disjoint. If you place it in U, you have to place the adjacent node 1 and 2. 2 is also adjacent to 0 in V. But since there is an edge between 1 and 2, therefore it will not be bipartite. If you did not have this edge, then it will be bipartite. If you did not have this edge, then it will be bipartite as well. Okay, and we have already seen the BFS code implementation of checking if a graph is a bipartite graph. So I think it is clear till this point. Now this question is not just about finding out if it is a bipartite graph, but the main part of the question is finding the maximum number of groups in which you can divide this graph. Well, the division is only possible if it is a bipartite graph. So the initial part of our problem was to check if it is a bipartite graph or if it is not a bipartite graph. So if it is not a bipartite graph, we will return a -1 according to the problem statement. But if it is a bipartite graph, that means we can divide the given graph into groups. Okay, independent and disjoint groups. So now we know that we can divide it into independent and disjoint group, but we have to maximize the number of groups in which we divide. Well, there are multiple ways in which we can divide. So let's say that I started dividing or assigning the group from node number 1. So if you start assigning from node number 1, you will place it in, let's say, group 1, and then all the adjacent nodes will be placed in group 2, and then their adjacent nodes will be placed in group 3. This is how you will try to maximize the groups using the level order BFS. So you can start doing the level order traversal from this one, and you can easily assign all the alternate levels with +1 group, right? Starting with level 1, this is level 2, and this is level 3. So there will be 3 groups. And I have all exactly written for group 1 you have 1, for group 2 you will have 0, 2, 3 in the next level, and for group 3 you will have 4, 5 at the next level, right? So this is how you can use level order BFS to find out the maximum number of groups starting from a given node. But maybe starting from this node 1 is not giving me the maximum number of groups. Maybe if I try from somewhere else, I will get even more groups. Let's try from 2. Now if you perform level order traversal from node 2, then this will be in group 1, and all its adjacent node, this one, will be coming into group 2, and all their adjacent node will be coming in group 3. So this is forming 3 groups, right? So you can just adjust these values. In group 1 you will just have 2. In group 2 you will have 1, 4, and you will have 5, right? 1, 4 and 5 in group 2. And then in group 3 you will have 0, 3 because it is at the 3rd level, right? So this is how you can perform level order traversal. But then if you perform the level order traversal at 4, you will be finding it in group 1. You will be finding this 2 in group 2. You will be finding this 1 in group 3, this in group 3, this will be in group 4, and this will be in group 4. So you are getting 4 groups starting from 4, and also starting from 0 you will get 4 groups as well. So that is why we may have to actually try level order BFS to find the maximum number of groups starting from each node, and then take the maximum of all these count of groups. So if we start at this 1, I was getting 3 groups, at 2 I was getting 3 groups, at 0 I was getting 4 groups, from 4 or 5 we will be getting 4 groups as well. So out of all these, the maximum groups are 4. So I will be saying that in this case we can divide this entire graph or component into 4 different groups. So the answer will be 4. So we can perform the level order BFS for each node to get the level count and take the max of all the level count. So I think finding the maximum number of groups is clear using level order BFS. Now this was just for one component. How to do it for multi-component graph? Now in the multi-component graph, I will again be doing the same thing. Try the level order BFS from each of the node, and I have already made the maximum distance array where I will be tracking all the maximum number of groups I can form. Like from 0 I can form 4 groups. This will be group 1, 2, 3, 4, right? So that is how I have 4 groups. From 1 I have 3 groups. So this is 1, and this is 2, and this is 3. Using the level order BFS, count the levels. So like this I have marked all these values. Now we have a second component 6, 7, 8. If you find out the number of levels from 6, this is level 1 and this is level 2. So 2 levels, so 2 groups. For 7 we have 3 levels, 1, 2 and 3. 3 levels, so we have 3 groups. For 8 we have 3 groups, 1, 2 and 3. 3 levels, so we have 3 groups. Now after doing this, for this component number 1, take the maximum number of groups, which will be 4. You can just iterate through this entire maximum distance and find out, it will be 4. For the other component, take the maximum number of groups, it will be 3, right? So what I will do is I will give it group number 1, this one, group number 2, group number 3, group number 4. Now for this I will be giving group number 5 instead of giving any other previous group, because I want to maximize the number of groups, right? I will be giving this group number 6 and I will be giving it group number 7, and all my conditions will be followed. So I have a total of 7 groups, which is found by the count of maximum levels in component number 1 plus count of maximum levels in component number 2. So it does not matter how many components you have, but you can just take the maximum level count and actually add it for each of the component. So for component 1 max level count was 4, for component 2 max level count was 3. So add them and you get 7 groups as answer. So this is how you solve for multi-component graph. So if I have to summarize the entire algorithm step by step, then step number 1 is to get an edge list and build the adjacency list in time order of v plus e. In step 2, check if the graph is a bipartite graph. If the graph is not a bipartite graph, you return -1 and you finish your entire algorithm. Otherwise, if the graph is bipartite graph, then it is possible to find groups. It is possible to divide the nodes into groups according to the problem statement constraint. So now we will proceed to step number 3. Calculate the maximum distance, that means the maximum levels from each of the node, and this can be done by performing BFS from each of the vertices, and the BFS takes v plus e time. So this will be taking order of v into v plus e. Now the step number 4 is add the maximum distance or the max level count for each of the component to get the maximum groups, and this will be just an iteration over the entire array. So this will be taking only order of v time, right? So the entire time complexity will be, all of these complexities will be added because all these steps are done one after another. So the total time complexity will be defined by step number 3, which is the most time taking step. So order of v into v plus e, and the space complexity is order of v plus e. You can check it out. Now in the constraint it was mentioned that the maximum vertices will be 500 and the maximum edges will be 10 to the power of 4. So we can say that v plus e will be approximately 10 to the power of 4 because 500 is significantly smaller than 10 to the power of 4. So if you write a v plus e algorithm, then that is going to be 10 to the power of 4. But if you write a v times of v plus e algorithm, it will be 10 to the power 4 times of 500, which will be 5 times of 10 to the power 6, which is less than 10 to the power of 8. That means it is going to run well within 1 second. So this is the entire approach, and I hope you were able to understand it. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. Now this is the driver function, the magnificent sets, and here we are given the edge list and the number of vertices. So I'll be making the adjacency list. This is step number 1. Make the adjacency list. Then I will be checking if the graph is bipartite. I have already shown this part of the code previously, right? How to find if a graph is bipartite. You can just check it out. If the graph is not bipartite, return -1. If the graph is bipartite, go to step number 3 and calculate the maximum distance from each of the node using level order BFS. So I will be defining a maximum distance with a value n+1 to capture all the nodes from 1 to n. And then for each of the node, I will be counting the number of levels in the BFS call, and I will be saving it in the max distance array. So how we are doing this? It is done by simple BFS call. So if you check it out, here we are doing the count level. So this is just a simple level order BFS traversal where we are getting the source node from where I want to perform the BFS, taking the visited array, pushing the source node into the queue and marking it as visited and counting the number of levels. And once we are done with level count, we are returning the number of levels. Okay. So this is the part where we are counting the levels for each of the node values. And after this, for step 4, we will be finding the maximum distance count per component. So we are again taking a visited array, and then we are finding the total levels. That means the total groups in which we can divide this entire given graph. And I will be iterating for all the nodes one by one, and I will be finding the total level. So first I will be calling the find max levels BFS. What this will do is, if you have components, let's say 0, 1, 2, then it will be finding what was the maximum distance from 0. It was 2, because you can divide from 0, you can divide it into 2 different levels. From 1 the distance was 3, from 2 the distance was 3. So I will be going iterating to each of these node and getting all these level count values and taking the max value out of it and returning as an answer. So 3 will be returned in this case. For this component, 3 will be returned as an answer. So the visited array actually helps us to say that if there is a node 3 and node 4, node 5, 6, so on, then are these also checked or not checked? Okay, if one component is covered in one call to find max level BFS, all these nodes will be marked. So if I again, if I had started from 0, okay, all these nodes are marked. If I go to 1, it is already marked, so this will not be called because it is already visited. And again 2 will not be called because it is already visited. But again when we go to 3, again the call will be made and we will cover the separate component, right? So if I can show you the find level BFS, then this is also a BFS code in which I am iterating through all the nodes starting from the source node where I want to start my BFS for the given component, and I am going through all the nodes of the component and tracking the maximum distance for each of the node and returning the max level as an answer, right? So this is a simple code. All the codes I have written in BFS. And finally, once you have added up all the max levels for each of the component, return the total levels as an answer. This will be the maximum number of groups in which you can divide the given group in such a way that it follows the problem constraints. Okay. So I hope you were able to understand it. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. Like and share our video and subscribe to our channel in order to watch more of these programming videos. See you guys in the next video. Thank you.